Welcome to Higher Structures seminar series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Kürşat Sözer, and he will tell us about braiding self-equivalences with bordism. And we thank Kürşat for agreeing to give this talk. So please, Kürşat. Yeah.
Thank you for the very nice introduction. And before starting my talk, I want to thank for the opportunity to present my work here in Feza Gürsey Institute Higher Structure Seminar. My work with Ian Hambleton and Robin Sroka, where this work mostly done when I was in McMaster under Ian Hambleton doing my postdoc, and another postdoc there was Robin Sroka. He's now at Münster, and I'm at Lille, and we're about to finish the project soon. It will be available soon, hopefully in a month or so. And yeah, I'm going to talk about homotopy symmetry spaces of manifolds, morely high dimensional ones, and its relationship with algebraic relationship with bordism theory. And this talk is mainly in between homotopy theory and geometric structure and geometric topology. So it's a really nice flavor between algebraic things in the homotopy side and also geometric things in the bordism side and surgery. So let's start. So before diving into details or things, I want to give a big idea or picture of what this project is about and how it is inspired one by one. So we want to understand the spaces of homotopy self-equivalences of manifolds. So for us, manifolds are closed-oriented connected manifolds of dimension 4 or above. And by homotopy self-equivalence in this talk, I mean those orientation and base point preserving. Ones, and for us, the notation is going to be like this. And what is the point? Like, we want to study this space, and we want to understand it algebraically, or we want to compute, if possible, using bordism theories, which are more computable. For example, we are going to fix maybe another space, not necessarily manifold. So what is a bordism theory for those things? Is like some manifolds of certain dimension, and they have some stable normal bundle to n, and we have a fibration. We are going to study these manifolds n with a map to this m prime. Like, we are studying cobordism theory associated with m prime and a fibration over BSO up to some cobordism relation. So this is everything roughly. I will make everything more clear later, but this is the idea. On one side, we have homotopy self-equivalence of manifolds, higher dimensional manifolds. On the other side, bordism. And this has been studied before in 2003 by Hambleton and Kreck. And we want to understand that and generalize it and even ask, where does it come from? Is there a further deep structure which gets their results? So in their paper, they have this braidings of bordism groups, which are braided with pi 0 of these spaces, pi 0 of homotopy self-equivalences. Like, what does that mean? Like, we have this space consists of F is M to M, which is base point and orientation preserving homotopy equivalence. And here, what is B? Like, in this case, in their work, they consider only 4-dimensional manifolds. M is 4-dimensional. And B here is a normal 2-type. So it has the same homotopy data of M in dimensions 1 and 2. And then this is like a comparison map of the half dimension of M in 2. And this comparison, the efficiency, is measured by somehow certain bordism theories. or computability of this thing from the half dimension is measured from using bordism theories. So what is the main idea of the talk? Is the spaces of certain self-equivalences of these higher dimensional manifolds fit into highly Cartesian square whose corners are homotopy self-equivalent spaces and bordism theories. And when we take its homotopy groups of this square, we are going to get such a braid and its generalization. Here we have only four-dimensional, they have only results on four-dimensional manifold. And they consider homotopy two types specifically. And they study pi zero of this homotopy self-equivalences. So one may ask why we try to understand or compute this.
So excuse me, by a braid, you don't mean a usual braid of several strands in free space?
No, no. Okay. I don't mean anything geometrical. I mean there are exact sequences. There are exact sequences of groups which are braided, like we will see.
Okay.
I don't mean anything in knot theory until now. We don't have knot theory or braid group or things. By a braid, I mean braid of exact sequences, like certain interlocking braid of exact sequences. So what is the motivation to study this homotopy self-equivalences? We have an oriented manifold. We associate to a space. And why one wants to study this space? By this space has a special more structure on it. It's in particular is a topological monoid. If we take two elements in the space, we can compose and get another homotopy equivalence. And in fact, this operation is homotopy invertible. When we take the pi zero of the space, it's a group like H space, pi zero is a group. And this is another most important, maybe the motivation is this is the inherent homotopy symmetries of this manifold. So in particular, when we pick a manifold, topological manifold, one can study homeo of M, like homotopy, homeomorphism symmetries. One can study diffeomorphism symmetries. And more weaker, one can study homotopy symmetries, homotopy self-equivalences, spaces of homotopy self-equivalences. And the things that we use in this work are kind of related, not quite, but somehow the ideas are related with surgery classification of higher dimensional manifolds. For example, we have a structure manifold. When we fix M in higher dimension, we have a structure group, which is the list of all manifolds which are homotopy equivalent to M. Like in higher dimensional classification of manifolds, what one does, one takes a manifold and considers all other manifolds which are homotopy equivalent to M. Like how many manifolds are there in the same homotopy class, on the homotopy equivalence class. And so in particular, the pi zero of this space, automorphism that we denote, our notation for pi zero of this space is automorphism. This automorphism group acts on this space. And elements of here before is a manifold and a homotopy equivalence. Now, when we take the orbit space, it's precisely those manifolds which are homotopy equivalent to this one. It's like if you understand this automorphism group, and then we take the orbit space of the structure group, we get a precise classification of manifolds. And these things are, in particular, as a property, maybe not easy to compute in higher dimensions. In lower dimensions, maybe. In higher dimensions, they are not easy to compute. There are a lot of works in the literature on pi zero. There are a lot of works in the literature on pi zero automorphism computations. But in this work, in particular, we also study pi k's, like SK symmetries of self-equivalences. And these things may encode more geometric data about the space or some homotopy data of space, but I don't have any idea about what type of information that this higher family of self-equivalences encode. So our guiding question was, can we understand this space using bordisms, normal data, and surgery methods? So in fact, these three things are kind of in this progress, in this type of thing, they are really into each other. They're intersecting with each other. Like when we do a surgery, we get a bordism. This is like this is a well-known thing in the H-cobordism theorem, S-cobordism theorem. When we make a surgery on a manifold, we get a trace cobordism. But in fact, this cobordism preserves this normal structure, and by normal data, what do I mean? By normal data of M, I mean its stable normal bundle, BSO. So this is the limit of BSO n, and this is the stable normal bundle. Stable bundle of M. So what does that mean? We embed M. M is n-dimensional manifold. By Whitney embedding theorem, we can embed it in higher dimensional space where K is very large. And we have a tangent space of M. And in this embedding, once we choose an embedding, we have a normal bundle. And that normal bundle data measures how the manifold twisted. So we have this normal bundle of M and K, dimension K. And when we stabilize this, we take this, we consider this embedding in our n plus k plus 1, we stabilize it in higher dimensions. So when we stabilize this, of course, in the k at least maybe, this is going to be trivial bundle over n. So they also have a relationship with Cartesian classes and so on, but what is this normal bundle data? How the manifold is embedded in Euclidean space, independent of the underlying dimension of the Euclidean space. So we embed in really huge dimensional and Euclidean space. So this embedding has some inherent twisting structure of the manifold that stays constant under the stabilization. So this data is about how the manifold is embedded, how twisted the manifold itself. And of course, when we ask these questions, before than us, in the experts in surgery theory and geometric topology, Ian Hambleton and Matthias Kreck, in 2003, they studied they asked this question, and in dimension 4, they get this braiding. When they pick a 4-dimensional manifold and it's normal 2 type, they get this braid, which relates pi 0 of the space, the homotopy self-equivalence group of a manifold, with certain bordism groups. And from now on, and then when we were in McMaster with Ian and Robin, we were asking this question, like, why does this braid appear? Or maybe our first question is, instead of M, can we generalize to higher dimensions? That's the first question we ask. And then we add another question, can we generalize the higher homotopy groups of this homotopy self-equivalence space? And later on, when we study these two things, we come up with also, like, we also answer these two questions. Like, where is there something that braids comes from that? Is there a conceptual explanation for this braid of this relationship between self-equivalences and cobordism on the bordism theories? And we answer to these questions as follows. This braid works in all dimensions above 4, or manifold dimension, and it works for all homotopy groups. And also, we have a conceptual explanation. Where does it come from? It comes from something homotopy-theoretical notion. It's a higher Cartesian square of spaces. So this is so far it's like a big idea of what is going on. We fix a manifold, we consider a space of homotopy self-equivalences, and then there is apparently some connection with certain bordism theories. Now I want to go step by step, clarification of everything, one at a time. So this space itself is very complicated and hard to compute. Pi zero maybe in some cases, but the space itself is hard to understand. Maybe for one types k pi n, they are understood completely, but other than that, we don't have so much understanding of the space itself completely. There are a lot of work on this rational type in special cases, rational homotopy theory approach to these spaces or these automorphism groups, but in this talk we don't have any rational homotopy theory part. But without rationalization, it's really hard to study. So to be able to study, we want to add some more algebraic structures, like, for example, using surgery theory and normal structures. And then to make it more computable, at least, we add some extra structure. We all consider certain subspace of this homotopy self-equivalences. So what we do, we consider subspace that preserve the normal bundle data, stable normal bundle data up to controlled level. We fix a parameter and we consider the nth Postnikov stage of the normal bundle. So as I said to you before, we have, and in this talk, I always write BO, but I did this before preparing the slides, and then I should have done at the beginning maybe BSO to simplify it. But everything you can consider BO, you can consider BSO. So this lifts, we have a vibration here. Since M is oriented, this lifts. Now, in the paper, we consider more general spaces and then we fix BO. But in fact, in this talk, I consider only oriented manifolds. So every stable normal bundle actually lands in or lifts to BSO. Minor detail. So we have this stable normal bundle data, which encodes kind of the data, how the manifolds embeds or twists in it's embedding its twist under like an invariant under the normal stabilization in our higher dimensional array. And we compose this map with the nth Postnikov section of BO or BSO. And we call this composition gamma L. It's just a map from the manifold, a continuous map from the manifold to nth Postnikov section of BO. And we define the naive space instead of M, which remembers the manifold and also this map, the data of this map. So how do we define? And then, okay, when we define this thing, and then we study homotopy self-equivalence of this normal data of this space. In particular, like what like in extreme cases, what happens? I guess, is there a question? There's a hand raised.
Yes, just sort of for reminder, for different values of L, say L1, yes. L2, how was the L stage or L stages are related as L changes?
Yes, like that's what I was going to say actually. Yeah, what happens when we move this parameter? When this parameter is 0, what do we get? We get precisely this complete space of homotopy self-equivalences. Almost no bundle data, because we just take the pi 0 to Postnikov section, which doesn't have any information except the connectedness. In the 0 case, this parameter 0 case is just the usual space of homotopy self-equivalences. In the infinity case, that then it becomes precisely BO, and this map is precisely nu M. So this space is going to be M nu M, which means those homotopy self-equivalences of M, which commute with the stable normal bundle. So in the L0 case, it's just the usual, the huge space of stable homotopy equivalences. When we increase L to infinity in the limiting case, it is the space of self-equivalences which preserves the stable normal bundle. Like these things are commutative diagrams. That's kind of the thing. It's like filtration. And so this space.
Is the normal bundle related to the principal bundle too?
No, this is vector bundle.
Okay.
This is vector bundle.
But
there's a stable vector bundle. You can consider it's a topological K-theory class. One can study those things.
Okay.
More than principal bundle.
Was it also related to the principal bundle of the manifold?
Principal bundle of manifold over which structure group? Like which group? It is related to tangent bundle.
Okay.
The manifold has a tangent bundle. This is the complementary of tangent bundle. This is a direct segment which trivializes. But manifold has the canonical thing that when we have a manifold is a tangent or cotangent bundle. The tangent bundle has the dual. The normal bundle is the dual of it in the sense that their direct sum, Whitney sum, is the trivial bundle. So this space can be considered as those homotopy self-equivalences which are like of gamma L, like, or of the homotopy. So those homotopy self-equivalences which commute with this gamma L, which is the composition of stable normal bundle with the Lth truncation of the classifying space. So what is this ML? I told you we have this thing which preserves both M and ML. So what is that? That is the homotopy pullback of this gamma L with this truncation, Postkov truncation. So what does homotopy pullback means? In the usual pullback, that means those points in M and in here which they match in here. In the homotopy pullback, we just make a thickening of this space. So it consists of a point in M and a point in BO and a homotopy in this space and a homotopy in this corner, which relates the images of these points. Not exactly they agree, but they agree. There's a homotopy between things. So this is called homotopy pullback or homotopy Cartesian square, one can think of. So what is the property of this thing is that we can consider homotopy fiber of this map and a homotopy fiber of this map. They are homotopy equivalent when we do this. Or similarly, horizontal. And if you remember, whenever we have a homotopy pullback, the maps to other spaces from homotopy pullbacks are equivalent to maps to their legs, such that this diagram commutes. This is still valid in the homotopy pullback case, but still up to homotopy. The map, this F from M to M, is this data of map is equivalent to giving a map in here and another map in here, such that their composition is not equal, but there's a homotopy between. Like giving this map is equivalent to giving three information. Two maps and a homotopy. And this is precisely this space. It consists of those maps such that this composition is a homotopy equivalence, homotopy self-equivalence of M. This side is homotopy self-equivalence, and this side is the stable normal bundle. And in this talk, the thing is, this side of the homotopy leg is going to homotopy self-equivalences. This side is going to be bordisms. We will see later. So, due to time, I can go a little faster here. What is the BL space? So instead of working with M, we look at its Postkov truncation, Alt Postkov truncation, not only Postkov Alt truncation of BO, but also M. So we apply the in a functorial way, we apply the stable normal bundle to this thing. So we get a map from PLM to PLBO. And then we take homotopy pullback of this diagram. So bottom does not change, bottom part, but this part, instead of M, we have now its alt truncation. Like in the previous case, we considered whole manifold. Now we consider its alt homotopy data. And we take a homotopy back, and then we define in a similar way the space of homotopy self-equivalences of this BL, which consists of those maps, such that this map is going to be L+1 equivalence. And this side is still stable normal bundle, because we want to keep the stable normal. And this is what I said is the same way. This space, by definition of homotopy pullback, consists of triples. A point in here, element in here consists of element in here, and the homotopy between their images in here. It's like a thickened version of usual homotopy pullback. And this is a kind of small result that this space, in fact, weak equivalent to homotopy self-equivalences of Postikov truncation of L, Postikov truncation of M, up to homotopy commuting with this alt normal bundle data. Remember, this new L is precisely functorial application of alt truncation to stable normal bundle. So when we have ML, we consider these triples, ML. When we have BL, we consider its alt truncation. And in fact, so far we studied these two diagrams of homotopy pullbacks. The first one was this one. The second one was this one. But there's a theorem in this homotopy pullback. If we have these two are homotopy pullbacks, then this is also a homotopy pullback diagram. It's very nice. And when we have a map in this space, we can push to this BL space. This is just composition with this map. So we have a map from M to ML, whose this side is going to be new M, whose this side is going to be homotopy equivalence. So when we compose this with this one, we get this map, and this composition is going to be L+1 connected, because this is already homotopy self-equivalence. So it induces isomorphism on all homotopy groups, but in fact, it's induces homotopy equivalence on all levels. So it induces isomorphism on L+1, first L+1 homotopy groups. So we have this comparison map, with just composition of maps with PL. So this is the two spaces, two certain space, space of homotopy self-equivalences that we associate the manifold and the level. So we have maybe here I can recap. We have a 4 or above dimensional manifold, and we fix a parameter. From this, we associate ML and BL, and we associate corresponding homotopy self-equivalence spaces, and a map between them, comparison map between them. And maybe I can repeat again. This space consists of those homotopy self-equivalences of M, orientation preserving, and also preserving the stable normal bundle up to level N. And this space is the homotopy equivalences of PLM, preserving the normal bundle data up to level N, level L. And we have a comparison map. This is like forgetting map. This forgets data, normal data of level L larger than L. So next we study bordism spaces. We associate to this space the bordism space.
Can you, if we have time, can you go back to one slide more? I just missed the Cartesian square. So the second square, the second two squares on top of each other, the lower
Yes.
diagram, we obtained it by breaking, somehow splitting the diagram above? Is that how it is? How did we construct those? I mean, those maps come for free, or they come from a certain splitting or a factorization of sorts?
Yeah, in fact, yes. It comes from a splitting. We have this Xi map, we have this outer diagram, and we have a lower diagram. So this map is gamma L. This is, in fact, composition of L section with the new L. And this is, in fact, more postfactorial factorization of this map. It's where it comes from that I didn't tell. This is a more postfactorial factorization of this map that gives us this map, this diagram. It strictly commutes, in fact. This side is strictly commutes. And this side is homotopy commutes, and outer diagram is also homotopy commutes. But it comes from this factorization, more postfactorial factorization. Next.
Thank you.
Yeah, no problem. Thank you for the question. So the next thing is the bordism spaces. So we have, so I didn't specify, but these things, whenever we have a pullback, these legs are always vibrations. So we have this vibration and this vibration coming from two pullbacks. So whenever we have a vibration over BO or BSO, one can associate the Lashow bordism theory. So what does that mean? It's like n plus k dimensional bordism theory for this space, which is a space which is vibration over BO. So it consists of pairs, and we have BO and ML. It consists of pairs where the first one is closed-oriented n plus k manifold, and the second, it has a stable normal bundle map. We have this vibration, and we have this lift. This diagram commutes. It's a lift of its stable normal bundle. It's those closed manifolds whose is embedding compatible with this vibration. There's a lift. And two things are coordinate if we have, two things are coordinate if there is the compact oriented one-dimensional above manifold with a map to this ML such that its stable normal bundle commutes with this. And the boundary restrictions are compatible. So whenever we have a vibration over BO or B top or BSO, one can associate a one can associate a stable Lashow bordism theory. And in fact, these bordism groups, this whole collection of bordism groups, they assemble into a spectrum, that omega spectrum. That means the first element in the omega spectrum is infinite loop space. It is, we denote like this. So its kth homotopy group is this bordism group. This is a group under disjoint union. This group is precisely the kth homotopy group of the spectrum, omega spectrum. So far we define everything for ML. One can define everything for BL using Xi tilde. So we are going to have BL in here. We are going to VL in here. We are going to have BL. One can define the same cobordism groups for BL, just as in here. Same way. It's a lift manifold with a lift of stable normal bundle with respect to this vibration. And we have between these two groups for any index, we have a comparison map, which is again coming from this forgetting map. We have a lift of this to ML. We compose with this one, so we get this one. We get this map. This is precise forgetting map. In fact, this map comes from a space level map. We have infinite loop spaces. There's a forgetting map on this level. And then when we take homotopy pi k of, this map, this continuous map, we get this one. It comes from some space level map. So we get this square. We have two spaces which are certain homotopy self-equivalences, which controls the orientation data and normal data up to level L. And we have, on the lower side, we have infinite loop spaces encoding these vibrations. that come from ML and BL. So this is the main square that we have in the paper. This is the main result is going to be. So what does this map? One can ask. I explained to you these two maps. They are forgetting. They forget the normal bundle data information above L. They are just, these horizontal maps are just forgetting the normal bundle information about level L. What are these vertical maps? So vertical map is, in this case, it takes a self-equivalence. It's a map like this, remember. It's a map into a homotopy pullback, such that it's one of the leg is nu m, and the other leg is homotopy self-equivalence. It takes this to this pair. It's canonical map. This is a space, so no equivalence class. Remember, there's a point in here. A manifold with a map to this, and then everything on the left commutativity of the diagram is precisely condition for this. And this diagram, indeed, since these are PL compositions, both this is a strictly commutative diagram. So the main result is for the manifold of dimension n or larger, closed manifold, and for k is larger than 0, and for L larger than this half dimension, this is the greatest integer function. It's the floor function. This square is homotopy k plus 1 Cartesian square. So the first question is, what does this mean? I told you about homotopy Cartesian square. It's like taking a homotopy pullback, but putting a homotopy. So what does homotopy k plus 1 Cartesian square? Like when we have a diagram, we have this, right, before above, this is the corner. So we can take homotopy pullback of this diagram, as we did before. It is this. Its point consists of a point in here, and a point in here, and the path in their images, connecting them. So this is the homotopy pullback of this diagram. So, and we know that when we have this diagram strictly commutative, so a map into homotopy pullback is equivalent to giving this information such that these compositions commute. And in fact, the homotopy. But since the above diagram is strictly commutative, in fact, the homotopy is just constant in this case. So giving this data, like what I want to say, this map exists by this commutativity. So k plus 1 Cartesian means this map is k plus 1 connected map. What does that mean? It induces bijection on pi 0. It induces isomorphism on homotopy groups less than or equal to k. And in level k plus 1, it induces surjection. So this approximates, so the idea is like we are approximating the homotopy pullback up to k plus 1 homotopy data. Yeah, we take pullback of L plus 1 normal data homotopy self-equivalences. We take bordism theories, and they are kind of they encode the same information as the homotopy pullback up to k plus 1 level. So another characterization of such a diagram is to saying that this is a definition, but it's hard to check. To prove this theorem, this is yes definition, but we use in the proof we use this characterization. So this diagram is k plus 1 Cartesian if the induced maps on homotopy fibers either here or here, doesn't matter. It's just one needs to check. Either this induced map in the homotopy fiber of vertical maps, alpha beta, is k plus 1 connected map. It's like this, same property. Or one can check the induced map on homotopy fibers of horizontal maps is k plus 1 connected map. This is to show a diagram is homotopy commutative, not to compute this thing, or what does the map does homotopy groups, but as I control, what has happened is the homotopy fibers. And we use this to prove this characterization. And in fact, this vertical diagram. Is there any question with the main theorem, maybe, before I can getting more into details? Okay. Next. Okay, at the beginning of the talk, I told you there is a braid. Everything started with a braid that is defined by Hambleton and Kreck in 2003. So how do we get from this homotopy-theoretical construction K+1 Cartesian square a braid of exact sequences? So in this case, we have a map. Like I just want to remind you, in the classical algebraic topology, is whenever we have a map, we can turn this map into a fibration, like path space fibration. So this has a homotopy fiber, like I should have written here, but it's homotopy-equivalence. So I abuse notation, but totally. So whenever we have a map, we can consider the homotopy fiber and treat this as a fibration sequence, and then we get a long exact sequence on homotopy groups. But in this case here, we have 1, 2, 3, 4 of them. That means we get 4 exact sequences in homotopy groups, right? Like in this case, we have the first one is going to be this one. Okay, let's see. This is this exact sequence. And then let's consider this one. This vertical one. Y, Z, this is exactly this one. And remember, yeah, and maybe I can comment on later, then we have this one. V, Y, it is this one, this exact sequence. And lastly, we have this homotopy sequence, homotopy fiber sequence, and it is exactly the third one. So these are the 4 interlocking exact sequences. They're coming from this homotopy square. But this thing works up to degree k+1. Because in the yellow and red one, we are using this homotopy fiber of alpha equal to homotopy fiber of beta, but they are only equal up to k+1. Right? So it works up to this degree. So the braid continues to the right, but not to the left. Like if this is index k, it goes to the until 0 level, but it stops at the k level. This is kind of maybe the idea or story behind maybe the braid. Where does it come from? So this is what I told. So this is what I written here is like a pure algebraic thing. In our case, what do we have? Oops. Yes, in our case, we have this diagram. Our homotopy K+1 Cartesian in here. We have a homotopy fibers. We have homotopy fibers in here. And we have exactly the sequences. And this is our theorem in the paper, the second theorem after the main theorem. So, and we have this half-dimensional constraint. This we will see maybe later. Why do we have this constraint? This is because to be able to do modified surgery theory, we need to have at least a half-dimension data to apply Kreck's modified surgery theory. So this braid starts from this level and continues to the right up to k=0. And when you consider n=4 here, this limiting case, and k=0 this case, the diagram is precisely, remember this, we don't have k, this is now pi1, this is now 0, this is going to be 0, this. And this is precisely Hambleton-Kreck diagram. Braid. When we restrict dimension equal 4 and k=0, so only 0-dimensional homotopy groups, so 4-dimensional manifolds, this must be then L min is 2, where they choose min equals 2. So this recovers their result in particular. That's what I want to say. And maybe here I can explain what is going on in this diagram shortly. For example, if we take a representative of this homotopy group, it's a map from k-dimensional sphere to this space. So what is this map under alpha? That is precisely its adjoint. Instead of S to K, because remember, this is a space to M to ML, elements in here, M to ML. So we're just doing adjunction to product, home product duality. And the same is in here. And this green ones be just composed with this PL. We push with the PL in the diagram. PL from ML to BL, the map, if you remember. On these diagrams, you push this. And here is the restriction to boundary. Again, we have restrictions to boundary in here. And here again, it's the adjunction between product and home. And you can check in each step on this diagram, this side, this side, this side, or this side. They're all exact. By hand, one can show they're all exact. So I can maybe quickly go with in the remaining 10 minutes. The idea behind the key steps in the main theorem. Remember, the main theorem says this diagram is k plus 1 Cartesian square. So, and we are going to prove using the second definition of k plus 1 Cartesian square. That means the induced map between these vertical homotopy fibers is k plus 1 equivalence. That means that induces bijection on pi 0, isomorphism on I is less than k, and a surjection on k plus 1. So there are two things we need to do. This is just purely homotopy fiber of this thing, this map. So the first step is to identify the homotopy groups of this space, this homotopy fiber, with certain bordism groups. And these bordism groups are defined as follows. They are those manifolds of n plus I plus one-dimensional manifolds, whose boundaries are I-dimensional sphere cross M, and they have usual lifting properties, and their boundaries satisfies the homotopy self-equivalence condition. So we have, like, this is a very low dimensional way of drawing it. It's like in dimension 2, it's like the boundary is Si cross M. We split the boundary into minus disk and plus disk cross M. On this minus disk, it's identity at every point. On this plus disk is any homotopy self-equivalence. And it lifts this stable normal bundle map of W. And two things are equal if there exists a homotopy behaving nicely. That is this formulation. This is inspired from the work by Hambleton Kreck. They have in 0 dimension. It's little different manifold. In this case, they have S0 cross M. We have now connected boundary, but things work nicely. In fact, the composition in here is really the composition in homotopy groups. I can show. It is a group homomorphism. So this equivalence relation is a little weird maybe at the beginning, but this is compatible with the group structure on the homotopy self-equivalences. So in the second step, once we understand the homotopy groups of, because we want to show that this map induces isomorphism on homotopy groups. So we identified homotopy groups of this thing with certain bordism groups. Next, what we want to do is, these maps are isomorphisms in this case, from these bordism groups that we define, like those spaces whose boundaries sphere product manifold and a map to be ML. So we want to do this, we want to show these things are isomorphisms and surjection for I plus 1. So everything in here can be defined not only for ML, but also can be for BL. Can do. And this map, what is this map? This is a homotopy fiber of alpha in the ith homotopy group. This is a homotopy fiber of beta in the ith homotopy group. This map is again composition with PL. So element in here, the first one, element in here is a manifold with a map to ML such that this diagram commutes. So we push here by composing with PL. We get this diagram commuting this one. So it's which makes sense because it induced from this map. This is also composing with PL. So quickly, maybe I can go. How do we show surjectivity? This is very cool. Maybe a little bit so much detail, but I will just spend 2 minutes, not more. So we get a map. We get an element in here, which is precisely this part. An m plus I plus 1 manifold whose boundary is Si cross M and a map to here. This is what we have. To show surjectivity, it's precisely lifting this map with respect to PL. That's precisely this. So if you look at the boundary of Z, right, we have this we have a sphere, Si cross M, but we split the sphere into disks. We glue 2 disks cross M along their boundaries. On this disk, we require this map to be identity at every point, identity of M as a homotopy self-equivalence, like a base point. So this map, this composition, in fact, induces for this property isomorphism and homotopy groups. But this diagram is commute, so it induces the same thing in homotopy groups. That means this G induces at least surjection on homotopy groups, because this part induces isomorphism. It must be at least surjection. This is apparently classical idea, like usual idea in surgery theory that I learned when I was at McMaster. So this is at least a surjection. It may be isomorphism, but let's treat it as a surjection at least. And then by doing Kreck's modified surgery below middle dimension, we kill the kernels by doing surgery. We find representative of kernel elements. We kill those kernel elements by doing surgery. And then we get a cobordism. We get an equivalence relation. We get another representative. We get a G prime maybe. We don't change the notation. We modified the map by doing surgery. We get a cobordism thing and a new map, but we just make it cobordism relationship. But that's in the same class. That doesn't change the start class that we start. We change Z to Z prime, G to G prime, but staying in the same class. So we make this map as isomorphism. So we make this L-min connected. We cannot go all the way to L because we can do this surgery up to half dimension. Then we study what are the obstructions to lift this new map to ML. That's precisely these groups. Like lifting a map from here to here is precisely the maps to homotopy fiber of this map. And these are the cohomology groups. And we are doing relative to this boundary because we want to lift that boundary to identity. But this thing, because this is L plus 1 connected, is L connected. That means this all vanish for less than L. And applying Lefschetz duality to this thing, generalized version of Poincare duality, we get a homology of this with respect to other boundary. But this homology is also vanishes because of this connectedness case. It's a little bit keeping track of indices because we go up to level half dimension, and then when we do this L-min connectedness, we get this number, this index is precisely smaller than what we had, so it vanishes. Because this thing, this is connected, and this map in collision to this induces isomorphism on this. All the obstructions vanish and then they. So idea for surjectivity is similar, and injectivity. And the remaining 4 or 5 minutes, I want to talk about some applications, nice applications. Barkus-Barat extension is a very nice computational one way of computing this homotopy self-equivalences at the pi0 level. Then we have a simply connected manifold. It is connected, simply connected, so we can assume in cell decomposition there is only one n-dimensional cell. Let's remove it and call the space M0. Then, so M is obtained by gluing a cell to this by F. So Barkus-Barat extension theorem says this homotopy self-equivalences of M, arbitrary ones, is sit into this exact sequence, where the left-hand side is those self-equivalences which are identity on this huge part. And if you consider this, these are kind of pinch maps. We take a manifold, we choose a small disk, we pinch it, and on this level we go identity, on this level we go homotopy groups. This creates this is called pinching homotopy self-equivalences. We choose a cell, we pinch, and then apply homotopy groups of the N. And the right-hand side is those homotopy self-equivalences of the remaining part, except this n-dimensional cell, interior of n-dimensional cell, which are compatible with the attaching map, which extends those homotopy self-equivalences on the boundary, which are compatible with the attaching maps. So Bao has used this in his remarkable paper, transaction paper, to show many things. Some of them are as follows. He showed that for simply connected Poincare complexes, this group is finite. And he made a lot of computations. Products of spheres he computed. And computed connected some, like products of different dimensional spheres. They connected some. He computed homotopy self-equivalence groups for n-1 connected to n manifolds. He also computes for metastable range, n-1 connected three n-dimensional manifolds, and so on. He has a lot of computations, a lot of ideas. And in our case, we generalize his theorem to not necessarily simply connected manifolds. But we had to choose this L quite above. When we have this assumption, then we have this exact sequence, which is again like those which are identity on this complement. But in this case, since our manifold is not simply connected, we need to encode this one-dimensional skeleton, which are like union of one-handeds or smooth manifolds. And in this case, those homotopy self-equivalences of L truncation preserving the fundamental class and so on. But this is a very similar result in this normal bundle data case for non-simply connected manifolds. And similar to this one, we also show when the fundamental group is finite, this side is also finite. So we kind of give a generalization in this controlled homotopy equivalences case of this Barks-Barrett sequence. And secondly, commensurability. Lastly, two groups are commensurable if they share a common subgroup of finite index. And so they are not the same, but they differ by finite index subgroups. This is a very common notion in geometric group theory. And more generally, G is called commensurable with another group gamma up to finite kernel if G has a surjection or the other way around. So it gets a surjection or gives a surjection out of it the surjection with finite kernel, and such that this thing is commensurable with gamma. In 2023, Bustomatic, Kreck, and Scoopers, they proved that for a finite CW complex, quite general, not a manifold, with finite fundamental group, simple group like pi0 of simple homotopy self-equivalences and homotopy self-equivalences of this finite CW complex, they are commensurable up to finite kernel to arithmetic groups. So this, I don't want to confuse this. They don't say these two are commensurable. They say this is commensurable, simple homotopy to some arithmetic group. This is also commensurable up to finite arithmetic groups, up to finite kernel groups. So they're not with each other, but they each individually. It's a really cool, very strong result. And along these lines, what we prove for n-dimensional manifold with finite fundamental group, and then we choose L in the same manner as before, like just 2 levels below its dimension, like preserving most of the normal stable normal bundle data maybe. This automorphism group, the pi0, this is precisely pi0 of epsilon dot ml. This thing is commensurable up to finite kernel with an arithmetic group. So we show this controlled homotopy groups like behave similarly in this assumption for finite fundamental groups. And that's all what I want to say. And thanks for your attention.
Thank you very much, Kürşat.
Thanks.
So I would like to ask a question. 2 slides before, you showed some short exact sequence. Yeah, these are like Galois group, right? I mean,
yes, it's kind of extension. One can see the extension, finite extension of. Yes.
These automorphism groups, they are non-commutative, right? Or they are commutative?
No, they are not commutative.
They are
Generally.
non-commutative, right?
This part is this is abelian. This is finite abelian.
Oh, that's finite and abelian. I see.
Yes, because they are like there's a surjection from higher homotopy groups of this complement to this one.
I see.
On this.
And this theory has connection with TQFT?
No. I mean, as much as I know, I know. That is.
I see.
No, this is more of. It doesn't have a connection, but maybe a little bit bold statement. It's like there's a very popular study of moduli spaces of manifolds, like, and by Galatius and Randall Williams and other people, very cool works, and they characterize this moduli spaces of deep M bundles, with also some infinite loop space of something. Our methods are different than theirs, but to me, the result, at least, so yeah, they show this space itself is some infinite loop space of some cobordism theory of normal bundle, some relationship. We have not equivalence, but we have we measured maybe the difference, the comparison difference. It's not the same, but maybe flavor. In terms of flavor, they are similar, I can say.
I see. And about the commensurability, those arithmetic subgroups appearing, that's quite, I mean, remarkable and interesting, because
yes, because this also, I can say, comment. Bowes, this paper is Bowes in 2000s, early 2000s, 1999, I guess, 2003. This paper, one can see that he computes this, and these are some SLN subgroups or their intersection forms. One can see this also in this case, in particular in his paper. For stable parallelizable manifolds, for example, or things he proves, they are intersection form. Some non-degenerate bilinear form.
Okay.
For these examples, and these are, if you look at, I mean, this is like this one, the example, this one,
right,
and connected to n minus one connected to n manifolds. And he give lists and diagrams for computations and groups, and yeah. So this, what I want to say, maybe short answer. This has a glimpse of that result, maybe a little bit. This exact sequence. Right hand side is like some subgroup of maybe arithmetic group or something.
Is there relation of this with this TMF kind of thing, like topological modular forms kind of thing?
I don't know, maybe. I don't know. I don't have any idea. And if there is a connection with TMF, then I can claim there may be a connection with TQFTs.
Oh, I see.
But what is the connection? I cannot estimate, because they have a connection with Euclidean field theories. Stones and fine there. That's a very deep theory. I don't know. TMF has connection with certain field theories, Euclidean field theories.
I see.
I don't know.
Oh, thank you very much. Any more questions or comments?
How about relation to mapping class group?
That's a great question. It's more
of a manifold.
It is maybe mapping class group more along the lines of this moduli spaces of manifolds, maybe, or also in three-dimensional case. maybe. But the problem is there may be some map from.
But I mean, there is
here
probably
to here.
Sort of.
Sorry, I couldn't.
Yeah, so then for the mapping class group too.
Yes.
Yeah.
Yeah. How does this map forgets or remembers? I don't know. I don't know the connection.
Okay, it's
because
I don't know
these things are more
either.
These things are more weaker equivalences. But what does weaker mean? Like preserving the purpose of structure and homotopy-theoretic equivalences. Yeah, I don't know.
But it could have a shadow in the mapping class group, right?
Yes, it may have. Oh, yes, I can maybe again. I can make a comment. I remember now. At the end of Bauer's paper, he has a connection with diff, with J homomorphism. He makes a connection with J homomorphism. So J homomorphism maybe relates this in some specific cases. Maybe some certain deep maps like J homomorphism or things which both appear in differential topology and at the same time the homotopy-theoretic equivalences may have. But Bowers, at the end of his last chapter of his paper, he has a connection along these lines.
Okay. And how about potentially functorial properties of the braiding exact sequence? Meaning, if you have two manifolds M and N, and there is some differentiable, some smooth map between them, maybe an immersion or a submersion, then how would the self-equivalences and bordisms of M and N would be related? Is that something?
That's a great question. We didn't thought about that, and I don't have idea. But my insight would be it is comparison along the bordism case, because if you look at definitions, like at the beginning maybe, where were we? Like these are really like comparing this with this is a stable normal bundle data of M. This is another manifold. Like this bordism theory kind of relates another manifolds with the normal bundle data of M, kind of. Maybe from that perspective one can do functoriality or something. But we didn't study that. It's a good question. Comparing two manifolds under some nice maps or something.
Right, because obviously the self-equivalences could, well, I mean, one can extend that question further than just diffeomorphism from M to N. What if we were to look at homotopy classes of diffeomorphisms from M to N or something like that?
Yes.
Maybe if one considers all the possible differentiable maps from M to N, that's a huge object. But if one cuts it down to classes of homotopies, then it might be a more manageable sized entity to study too. And it might fit into your framework better.
Yes, diffeomorphism is definitely stronger than being normal, this relationship. Because this relationship is like being bordened or normally bordened. It's like two manifolds are bordened, normally bordened if there's a surgery between them. If one can obtain from one to another doing surgery, it's like, are they normally bordened? That's a weaker question than saying, are they diffeomorphic? That is like going from surgery theory down to H-cobordism or S-cobordism, maybe. Yeah, that's something. Yeah. If we have H-cobordism, we have diffeomorphism between two manifolds, or S-cobordism. But the other side, I don't know more. Yeah, I guess.
Okay. And one more thing. Do you know about spectral sequences at all? So then this braiding, could it actually have been extended or coming from a sort of a page where there's a spectral sequence, and some spectral sequence analysis would descend to this braid?
Yeah, that's an excellent question. When we started this project, one of the things we were trying to do, Bowers has this many computations on spheres and products of spheres, and they're connected some things. He has a list of computations and things. So we asked how does this at least in the case of Hambleton Kreck paper, how computable it is and things. And this is, if you look at this part of the sequence, this is precisely homology being bordism being a homology theory. So this is a pair of exact sequence. So it's in fact, bordism is a homology theory. That means one can associate spectral sequence. Here's a spectral sequence. So we try to compute, for example, S3 cross S3. So 6-dimensional manifolds and things, and it kind of computes using spectral sequences. Like, because to compute the pages of this thing, this is the each page, and this is the kernel of this alpha map, and this is some higher data. But this most of the maybe things in the that appears, one should be able to compute from spectral sequence. Here's a spectral sequence associated with the homology theory. It can be computed, but it is my observation. It is little bit more. It is more work than this exact Barkus-Barrett exact sequence. So my comment on connection with spectral sequence is that there is kind of underlying here homology theory, which is a priori computable in some cases, maybe in some examples of manifolds, maybe Hopf maps and things. They're nice things. A priori, it may be computable using spectral sequence. Here's a spectral sequence, and from there, these things may be computed. Maybe if this is simple, this is computed. But the sequence, does it come from us? Is it an E2 page of some spectral sequence? I don't know. I didn't think along that path. Maybe that would give another conceptual explanation. But I don't know. I don't know.
Okay. And maybe last is, did you consider thinking whether this could, thinking very in terms of direct applications, whether it could have some applications towards interpolation type of problems in relation to topological data analysis? Not sure if you're at all familiar with that, but
I heard of it, but we did not do it.
Okay.
The interpolation, I can say, maybe the last thing I can say, the interpolation is when L goes infinity, these two things get closer to each other. Like the sequence expands or k infinity. These things they approximate each other even closer. And eventually, what does it compute? It computes to epsilon m nu m. Those homotopy self-equivalences preserving the stable normal bundle completely. But from computation point of view and that analysis, I don't have any idea.
Okay. Thank you very much. That was a wonderful
Thanks for
talk.
the question. Thanks for the question. Thank you.
Any more questions or comments? If not, then let's thank our speaker once more.
Thank you.
Kürşat, thank you very much.
Thanks for the opportunity.
2 weeks later, we will meet again. Who will be the speaker? I think we have a speaker from Kyoto University, I believe, as far as I remember. I have to check. But anyway, so we see you each other in 2 weeks' time. Bye bye.
Thank you.
Thank you, Kürşat.